Alrighty, welcome back, everybody. Hope you had a nice weekend. We're going to continue off talking about chemical reactions today. We're going to do a little bit more balancing practice, but remember that there is a lot of practice on our Canvas site for you guys, so definitely practice on your own too. We'll do a couple more problems here today before we move on to our kind of next um, topic within chemical reactions. So with that, let me just load this up real quick. Okay, here we go. So last time we talked about how to balance chemical equations. We did a couple of examples. What we haven't looked at though is balancing combustion reactions, and those are a little bit more difficult, I'll say, because if we just go ahead and look at it, of course the products for this would be CO2 and water, right? We do have oxygen in multiple places on this particular reaction, and that makes it just slightly more difficult. So when you're doing it, when you're balancing a combustion reaction, it's best to leave oxygen to last because it's going to be the more complicated one. But we're going to see that we can go ahead and do this, and I'll show you a few kind of tips and tricks we can use to make these a little bit more manageable. The real reason that these are more difficult than typical reactions to balance is because of that oxygen, because specifically it comes as diatomic oxygen in our reactants, but we have three oxygens in our products. That's the problem here. So we'll encounter that in a little bit. Let's go ahead and just record how many of each element we have to start, and then we'll deal with that pesky oxygen last. So if we are to balance carbon, we're just going down the list. We need 3 on the right side, on the product side. So we will probably want to fix that. So if we bump that to 3, we're going to now change our oxygen to 7. Notice that there are 6 from 3CO2 and then 1 from water. So that's 7 altogether. So that's, again, you just have to make sure that you're accounting for those oxygens every time you change something here. We can see with the hydrogen we are going to have 8 on the left, there's 2 on the right, so we need to make that into 8. If we need to do that, that means we need a coefficient of 4 here. That's going to now change our hydrogen, and it's going to change our oxygen again. If we do that, we see now we have 10 overall oxygens, 6 from the carbon dioxides, 4 from 4 waters. That's 10 overall. And if we go ahead, now we can see that we need to have a few more oxygens here. So if we want this one to be 10 as well, we're going to need 5 diatomic oxygen there to make it all balanced. And so that's how you would have your combustion reaction. This is propane, by the way. Perhaps you've heard of that before. If we do another example, we're going to see the next one we do is not going to be so nice to us. But any questions on this one before we move on to a slightly more complicated one? All right. I'm going to need more space there. Okay, so we've got our combustion reaction. Just like before, we have our 3 elements. Get our reactants and products. So my reactant is just a little bit too low. There we go. We see that we have 4 carbons, 1 carbon, 10 hydrogens, 2 hydrogens, 2 oxygens, 3 oxygens. Hopefully by now all of this is fast to at least get to this point. So let's go ahead and start our balancing. Start with carbon like before. We can bump that up to 4 to make that carbon balanced. If we do that, we now have 9 oxygens. We have 8 from the 4 CO2s and 1 from our water. I'm just going to keep doing this just so we can see. That's why I have the oxygen like that. If you don't need to do this, that's totally fine. You can just put 9 and move on with your life. If we need this to be 10 as well, we're going to add 5 water, or we're going to change it to 5 waters. So now we'll have changed this. So this is going to be 13 then. And here we have that pesky problem. We have an even number on the left and an odd number on the right. The least common multiple for these two would be 26, right? 13 is a prime number, right? And so best thing to do is just kind of multiply them together, see what you get. You get 26. Once you do that, if we want everything to be 26 oxygens, if we want that to happen, if we want this to be 26 and this to be 26, well, we can put 13 there, but we're going to have to double everything else. So remember that the coefficients that we had originally written gave us 13. So if we double those coefficients, we'll get 26. And as you can see now, we have 8 carbons, so we'll just need to go ahead and double that one as well. And so we had to essentially double the entire reaction to get this one to work out. Sometimes what you'll see for this type of reaction, this is the way we want to do it, by the way. We want everything to be integers. However, sometimes you will see you might see this presented like this. This is not a way we're going to do it in this class. However, this is a balanced reaction. They just put a 13 over 2 there. That would balance out the oxygens by having 13 halves. That's 26 over 2, which will be 13 oxygens. So you may see things like this, but we're not going to do that for this class. So we want everything to be integers. This is technically okay, but for this class, make everything integers. The lowest possible integers. Okay, so with this, we would prefer our answer to be the one written kind of in the dark blue letters here. We want the 2, 13, 8, and 10 as our reaction coefficients for this particular example. All right, so there is, of course, a way to get around this. Let's write it in purple. For combustion reactions, if you double everything at the start, you can avoid similar problems. But then, as a result, there is one more thing you need to keep in mind. But you need to make sure you have the lowest integers. So, for example, take a slightly different hydrocarbon. What we can do is just double everything right away. If we just put 2's on everything to start, before we even start counting up our atoms, that can avoid the problem of the oxygen having an even number on one side, odd number on the other side. We can get rid of that right away. But we're going to see for this one, we'll do 2 more examples. So for this one, we're going to see that, actually, let's hold off on this one. Let's do this one after. Let me do a different example first. Just gonna cut this one. Let's do this one right now, actually. Alrighty, reactants and products. So if we just double everything right away, we can go ahead and count things up. We see we have 10 carbons for our reactants. We have 2 carbons for our products, 20 hydrogens, 4 hydrogens, 4 oxygens, and say 4 plus 2 is 6 oxygens. So notice everything's an even number here. We've gotten rid of that problem of having odd numbers. Actually, I've been doing light blue to be consistent here. So let's just go ahead and balance this. If we need this one to have 10, we're going to need to change this coefficient to 10. So we have 10 carbon dioxides now. So that means we have 20 oxygens there. And then 2 from water brings us up to 22. We have 20 hydrogens on the left. We have 4 on the right, so we need to make this one into 20 as well. By just changing the coefficient. By doing so, we now have 30 oxygens overall. And so if we want 30 oxygens, we just need to have 15 of the oxygen gas. That'll give us our 30 oxygens, and we're done. So we were maybe able to save a little bit of time by doubling everything first. So that allowed us to get to our coefficients without having to worry about running into those problems with odds and evens and all that. So by doing this, we were able to kind of just skirt through that, and we win. All right, so as a result, we can do it this way. We end up with 2, 15, 10, and 10 as our coefficients. Any questions on that one? And those are all the lowest integers it can be, right? So what we're going to see in this one, when we balance it, we just have one more thing to keep in mind. All right, cool. So if we do this, we have 8 carbons, 2 carbons, 16 hydrogens, 4 hydrogens, 4 oxygens, and 6 oxygens. Okay. So doing this just like always, I guess I need to switch colors. I will be consistent. So we move this to 8. Okay, so then that's going to now give us 16 oxygens. 16 plus 2 will give us 18 oxygens total. We need to have 16 hydrogens on the right, so that means we need 8 waters. If we have 8 waters, we'll have 8 more oxygens. 16 plus 8 is 24. If we need 24 oxygens, then that means this number needs to be 12 here. And everything should be balanced now. But what we need to look at is that all these coefficients are divisible by 2. So we need to reduce them. So we go from, I'll copy this. We always want to just put the lowest ratios, right? So it's a ratio of 2 to 12 to 8 to 8, but we can instead bring that down to, hold on, one of them's trying to go out. So if we end up reducing them down, we can do that. The reason that we had to do that is because we doubled at the start. Half the time your combustion reactions will, you'll end up with an odd number of oxygens. In this particular one, we ended up with an even number if we were to just start off at the beginning. So that's just kind of the trade-off there. So if you want to start by doubling everything, just keep in mind you may need to divide at the end. However, sometimes the doubling just makes things easier. So it's up to you, whichever way kind of you like to balance these. So your answer for this one should be the second line there. So that's what we're looking for as an answer for this problem, for balancing this particular reaction. All right. So practice, practice, practice. Again, hundreds of problems are on Canvas for you guys to have fun with. So enjoy as much as you can. We're going to continue on now with kind of our next topic here, just looking at reactions a little bit more closely. Alrighty, so cool. Let's talk about now evidence of reactions. So, of course, early chemistry, didn't really have very many analytical techniques. They kind of just looked at things and said, okay, did something happen? And there were a couple of ways that they would be able to determine if something had happened over the course of a reaction. And we've actually seen a lot of these already so far through kind of the videos that we saw last time. We saw that sometimes we get what's called precipitation, which is the formation of a solid in a reaction. This typically looks like, it looks cloudy. That's a common one, or it becomes opaque, or gelatinous. There's kind of a change to the texture of the solution, as it were. So if you were to mix two things together and it becomes cloudy, that indicates you formed a solid. You just have very small particles in there. You're forming a colloid, essentially. And that colloid is just, remember, dispersing light around so we can see it. So as a result, it looks cloudy to us. So if you were to mix two things together and it forms a cloudy mixture, that is a precipitate. You are having a precipitation reaction take place. You are forming a solid. And we saw that many of our double displacement reactions can form solids when we look at our solubility rules. Another one is gas evolution. Obviously, that's formation of a gas. And we see that often we would just see bubbles taking place, or we might have things that smell. So bubbles would be something like CO2 or SO2. Those would be bubbles that we would be able to see as a reaction happens. Or we can have stuff that smells bad. Those would be like ammonia or hydrogen sulfide. Hydrogen sulfide is a rotten egg smell. Ammonia is, hopefully you smelled ammonia before. That's, it's a cleaning agent. Stinks, kind of fishy odor, a little bit. Those are kind of evidence that you would have reactions happening. If all of a sudden it's giving off a strange smell, that smell can only get into your nose if it's a gas. So you're going to be able to tell that a reaction has produced a gas, either if there's bubbles forming or if you start smelling things. These two are a bit more polar, the ammonia and hydrogen sulfide, so those tend to not make bubbles as much because they dissolve in water pretty well. But stuff like the CO2 especially, CO2 does not dissolve in water very well at all, so you see it forming bubbles right away. And that's pretty obvious, so you can tell something has happened there. Another type is what's called a neutralization, or acid-base. These will produce a lot of heat. And they will also produce water. Liquid water. So if you were to mix an acid and a base together, typically you get a lot of heat out, so things heat up very quickly, and you'll also produce a little bit of liquid water, so that may change your volume a little bit. So that's kind of another example of evidence. You'll see a temperature change associated with a reaction. And the last one we see is going to be a color change. Actually, let's kind of classify that a little bit separately. We'll call these redox reactions. We're going to see that those we'll talk about probably tomorrow. I don't know if we'll start that today. That just means electrons are transferred, and that typically presents as a color change, generally speaking. So we saw that reaction where we had the solution that was clear. We put the copper metal in it. We saw we produced silver metal out, and then we produced a blue solution. So we had done some color changing there as electrons were moved around. That's an example of what's called a redox reaction. We'll talk about those later. And usually you see a color change associated with those, if you're going to see anything at all. So with that in mind, these kind of four categories of reaction observations kind of just go hand in hand with what we talked with types of reactions. So with these precipitation reactions, you form a solid. With gas evolutions, you form a gas. With neutralizations, you form water or a liquid. And then the redox reactions we're going to see are kind of their own category. We'll talk about them later a little bit. And so with these, we're going to see that sometimes some components in a reaction don't actually do anything. So last time maybe we took a look at this reaction. we saw that this would produce sodium chloride and calcium sulfate. If we were to throw our states of matter on here, remember the calcium sulfate was solid because calcium sulfate is not a soluble ionic compound. If we were to balance this, by the way, we would just need a 2 there. See all the stuff I can give you? I can just give you 2 reactants. You can do all this stuff. This is a precipitation reaction, right? It's also it's a double displacement reaction in terms of how things are behaving, and it's also a precipitation reaction because we're forming a solid. So we kind of have 2 ways of categorizing this reaction. This is based on kind of the chemistry, and this is the kind of evidence that this reaction took place, is that it is a precipitation. So if we look at this more closely, and if we also remember that soluble ionic compounds are strong electrolytes we see, if I just duplicate this reaction, let's just copy it. If we want to look at what's really happening in this reaction, we can look at things a little bit more closely. Remember that if it's a strong electrolyte, a soluble ionic compound, it actually doesn't look like sodium sulfate in solution. Remember that these will actually split apart once you dissolve them. You actually end up with 2 sodium ions and a sulfate ion in there from that compound. When you dissolve it, remember, it splits apart. It's an electrolyte. It splits apart, it conducts electricity. So we know that these ions tend to dissociate, separate from each other once they are in solution. So in reality, that's what's happening there. We see that the calcium chloride, also being soluble, will also dissociate in solution. Let's see, am I going to run out of room here? I might, but let's, we'll try and get this. We see that we have also our sodium chloride being soluble here. But the last one we have in light blue is not an electrolyte. It doesn't dissolve, right? It's a solid. So those always come as their little pair, and they're not going to be separated. And so if we look at this reaction, we might notice a couple of things. What color have I not used? Let's see, how about we do, how about this kind of other green? Notice we have a few things in this reaction that are identical on both sides of the equation. That means they are not undergoing a chemical change. or thereby they are not participating in the reaction. They're just kind of floating around there. They're floating around in the solution. They're not really doing anything. However, we do see what's left over. Oh dear. However, we do see that what's left over in the reaction, everything that's not duplicated on the other side, is participating in the reaction. We call these things spectator ions. They aren't participating in the reaction. They're just kind of floating around there. They're helping to charge balance things. That's all they're doing. But they're not actually doing any chemistry. We see that all the chemistry of this reaction is kind of condensed to this kind of last little bit once we get rid of those spectators. So the spectators are just floating around, they're not doing anything. So if we just kind of move them away, we can look at exactly what is happening in this reaction. And we see that what's happening here, we have a sulfate ion and a calcium ion combining together to form calcium sulfate, the solid. All right, and so this is what is happening overall. We call this a net ionic equation. And that's just showing exactly what is happening and is getting rid of all the extra stuff. We're going to see that all these spectators here, we could replace them with any other spectator if we wanted to. We would see the exact same reaction would take place. For example, if we instead put K2SO4 plus calcium nitrate, we would still get calcium sulfate. And we would see that this would have the same net ionic equation. Hello, mister, you need to go out now. I'm teaching. I need you to go out. You're going to make noise. All right, so with this, if we were to look very closely at this, calcium sulfate we already saw was solid. We would expect calcium or potassium nitrate to be aqueous, right? Obviously because it's got potassium and nitrate. So if we look at these more closely, lots of writing for this one. It's not your food, mister. Oh my goodness. I have no space again, so I have to write down here. These take a little bit more space. All right, so if we notice here, we have things that are identical on both sides of the reaction. We have our spectator ions, therefore those are just kind of chilling in there, not really doing anything. And we see again the overall reaction, or the net reaction, is that combination of these two ions to form the solid. Okay, so with that, we see that Kaladin, mister, I need you to go out. Go on, go get out of here, mister. 1 second. Come on, Benny. Yeah, why don't you go outside? Yeah. Good boy. Alright, Miss Jersey, relax. Okay. So, looking at that, we see that these spectator ions, again, didn't really participate. We can change the compounds up, change our spectators, and nothing changes in our reaction. Overall, we're going to see the same thing happening. We're going to see a cloudy precipitate forming, and we'll be able to see that overall the reaction is exactly the same as before. We're going to see that we have, for solubility rules, that everything in that kind of first category, metal-wise, and then the acetate, are always spectators. I'm omitting ammonium from this because we are going to see that there is one case where ammonium will not be a spectator. But by and large, ammonium usually is. So with these, those ions are always going to be spectators. So thankfully, we can just kind of get rid of them. But we'll see that because those are always going to be soluble, they're always going to be ions, they're not going to ever participate in a reaction. So they're just there to charge balance things. So we'll see that very often these things we can just kind of dismiss as spectators. We can just swap things out if we really wanted. We could say instead, now let's put lithium sulfate plus calcium acetate. And guess what? We're going to get the same product. This time we'll have lithium acetate as the other product, but again, that's soluble compounds, so it's going to be spectators anyway. We're going to see that overall, our net reaction is exactly the same as it was before. So your spectators can change. Doesn't matter. But this reaction is the same. Oh my god, how many times I've written calcium. So, cool. So overall our reaction is the same for any of these. So we can just change out our spectators whatever we want. If we wanted to make calcium sulfate, we see we could mix all sorts of different things together to get calcium sulfate out as a product, which we could then just filter, and there we have it. Now we have our calcium sulfate. Hooray, we did it. We call these, as I said, net ionic equations, right? We're going to see that we have names for the other equations as well. But let's do another example first. Let's take a look at that, which one was it? We had the copper plus the silver nitrate that we did. Remember, it turned the solution blue. We did a 2 there. This is what's called a molecular equation, by the way. If we want to look at what's happening in solution, we do what's called a complete ionic equation. And that's where we separate aqueous things into ions. If we do that, copper changes. The copper solid is not an ionic compound. It's not an electrolyte. It's not going to split up. It's just copper. Obviously, we don't see copper dissolving, you know, because we use copper cookware all the time, right? We have 2 silver ions in there, plus 2 nitrate ions. Notice we have nitrate. We can tell already that's going to be a spectator, right? Nitrate is always a spectator. Oh my gosh, my aqueous gets uglier and uglier. There we go. Alright. So our complete ionic equation has everything now split up that was aqueous. If we're looking for what's identical on both sides, let's use the green, we see that the only thing that's identical is the nitrates. Obviously, copper solid and copper 2 plus aqueous are not identical, right? They are different from each other. Everything has to be exactly the same for them to be identical. We have 2Ag plus aqueous versus 2Ag solid. Those are going to be different, so we can't call them spectators. Spectators have to be exactly identical on both sides. So we have, in this case, we have nitrate is a spectator. For this particular reaction. And remember, that means identical on both sides. I don't know how to spell identical, it seems. Identical. And then we'll see that the net ionic equation is just whatever left over. So we just get rid of the spectators, we just put everything else that's still left over. Ooh, lots of work there, but we can see now overall exactly what's happening. So we can see that copper is going to react with the silver ions to form a copper ion and elemental silver. We're going to see that many single replacement reactions will have net ionic equations like this. But overall, what is happening here is this. The nitrate is not really doing anything except to kind of stabilize things and provide charge balancing. That's it. Nitrate doesn't participate in the reaction. All right, any questions on that one? We'll do another net ionic equation here, but there are, again, I think, like 12 or so practice problems on one of the worksheets on Canvas. One of the ones in the extra practice area, so you can kind of practice these and make sure that you fully understand what's happening here. Let's look at one more, and we'll do the complete ionic and net ionic equations here. If we go ahead and, what shall we do? How about we do, okay, let's take these together. We can predict the products. Hopefully we can see that lithium bromide will be one of the products. That should be aqueous, of course, because it's got lithium. It's also got bromine. Bromine tends to make things soluble. The other one we get from this double displacement reaction is the ammonium hydroxide. We should see that this reaction is balanced already. Thankfully, we don't have to worry about balancing it. Everything is just already done. But one thing we do want to note is that we never will write ammonium hydroxide. We have to remember that that's one of our gas-forming reactions. And so now let's go ahead and take a look at this. This is our molecular equation up top, right here. Let's look at the complete ionic. So let's take apart all of our aqueous things and see what's happening overall. So if we look at the complete ionic, this is the molecular equation, complete ionic equation here. We're going to have the ammonium ion, the bromide ion, a lithium ion, and a hydroxide ion. Lithium ion, bromide ion, plus ammonia gas, plus water liquid. Remember, only aqueous things get broken up. We leave solids, liquid, gases alone. So those don't change in a complete ionic equation. If we look for spectators now, do we have ammonium on both sides? We do not. Do we have bromide on both sides? We do. So bromide is a spectator. Get rid of it. Do we have lithium ions on both sides? We do. Spectator. Get rid of it. Do we have hydroxide ions on both sides? We do not. So we can now see that we can reduce this now to our net ionic equation, where we have the ammonium ion plus the hydroxide ion forms ammonia gas plus water liquid. And that's overall what's happening here. The lithium and the bromine don't matter. If we wanted, we could swap those out for any other spectators that we felt like. We could make it lithium chloride. We could make it we could make it ammonium chloride, ammonium acetate, ammonium nitrate, ammonium iodide, ammonium sulfate would work also. I mean, we have all sorts of different things we could replace with the ammonium there. Lithium we could also replace. We could make it potassium. We could make it sodium if we wanted, something like that. It would work. All right, and so overall we would get the same reaction out. So that's how we can kind of look at things in general here. Alrighty, any questions on that one? Alright, so practice these. You should see that some reactions have no net ionic equation. And that means no reaction actually takes place. For example, see all of these are aqueous. If we look at the complete ionic equation, technically we've got to write aqueous on all these things, don't we? So let's just copy paste that because I'm lazy. Alright, so all this stuff is aqueous, right? So we see both sides. We have potassium ions, we have chloride ions, we have hydrogen ions, we have nitrate ions. There's nothing left over, no reaction actually took place. So we see that this actually has no reaction that takes place overall. And so if we were to do this, we would not expect to see any evidence of reaction either. We're mixing two things together, nothing happens. We wouldn't see any evidence. There's no precipitates, there's no bubbles, there's no color changes, nothing. Everything cancels out. So as a result, we have no reaction taking place here. And so we can tell by looking at this net ionic equation. Right, so everything canceled out. No worries there. Any questions on that one? All right, so in summary, we have the molecular equation. That's kind of our normal one that we're used to. We see this plus this equals that plus that, or whatever it happens to be. That's our normal equation. We call that a molecular equation. We have the complete ionic equation. All aqueous components are broken into ions. And then our net ionic equation, all spectator ions are removed. And remember, for a spectator ion, means it's identical on both sides. Of the complete ionic equation. All right, so that's kind of what we've looked at today. So we've been able to see that we can generate a net ionic equation from a molecular equation by looking at the complete ionic equation and removing spectators. Remember, spectators must be exactly identical. If the coefficients, by the way, don't match up, it means you've balanced wrong. So that's a hint for you as well. So if you notice something that should be a spectator, like sodium or something, and it's not completely identical, that means you've done something wrong. So double check your balancing, double check everything on that. You should make sure that. Another thing to note is if you have, say, 2 sodium sulfates, if we're to break that up, that ends up giving us 4 sodium ions. Ions are always aqueous. Plus 2 sulfate ions. Just don't forget the charges. Don't forget your state symbols, the state of matter. And don't forget your coefficients. So notice that this 4 here comes from these two. And this 2 comes from that 2, right? So we have 2 sodium sulfates. Each sodium sulfate has 2 sodiums. So therefore we have 4 sodiums overall. We have 2 sulfates because each sodium sulfate had 1 sulfate. So just make sure that when you're breaking stuff up into ions, that you pay attention to the coefficient as well. So coefficients and subscripts matter here. So just don't forget about those. All right, so that's my kind of a last little hint for you guys. All right. I don't want to start the next topic, which is on the redox reactions, We'll start that tomorrow since we are pretty much out of time. So if there are no questions, then keep practicing. We'll continue tomorrow with more. We'll finish our chemical reactions chapter tomorrow, actually, by looking at the redox stuff. And then we can maybe start looking at math with chemical equations. But we'll see. So, cool. All right. And we're done for today then. So I'll see you guys tomorrow. Enjoy your Monday.